Swayam Prabha. Digital India. Educated India.
Welcome back to the series of manufacturing automation lectures. So, I will remind you that we were discussing in the last session, we started discussing the performance and economics of assembly systems. And we said that in case of indexing machines, the effect of part quality on downtime can be defined. For that, we have taken some parameters, and we said that the total downtime taken is mx and t, which is m is the proportion of defective parts causing machine stoppages, x is the quality level of parts, small n is the number of automatic workheads in the assembly line, capital L is the number of assemblies that we are producing, and the capital T is the time taken for an operator to diagnose the problem if the line stops or the machine stops and restart the machine. So, the machine time to assemble n assembly, if we know the cycle time is t, small t, so it will be n into t. So, therefore, we can find out the proportion of downtime, which is the downtime divided by total time, and the total time is assembly time plus downtime. So, therefore, it will be m n x n t divided by assembly time is n t and the m n x n t. So, we said that for standard fasteners it is somewhere around 0.01, 0.02 is the x, that is the quality level. However, if the quality level to be increased, for example, from 0.01 to 0.005, then we said that cost will be roughly twice. So, therefore, we have seen that there is a curve here. So, depending on the number of machines n 5, 10, 15 and 20, you can find out that more the number of machines, more will be the proportion of downtime, in one word. Okay. So, these results show why it is rarely economical to use indexing machines having a large number of automatic workheads, because larger the number of workheads, more will be the, for example, suppose you take 0.01 is the x. Okay. So, this is the quality level of parts. So, 0.01 x, this is the proportion of downtime for number of machines 5, whereas it is much more in case it is 10, even more when it is 15 and more it is 20. It is understood that more the number of machines, more will be the possibility of the downtime. They also illustrate why in practice it is advisable to allow for downtime when considering the use of an indexing assembly machine. What it means is that sometimes we may allow this downtime rather than defective parts going inside and spoiling the machine. Effect of part quality on the production time, let us see. In the preceding example, it was assumed that all defective parts fed to the automatic workhead should stop the machine. We said that the m is equal to 1, and in our earlier discussion we have seen that if m is less than 1 means not all defective parts will go and stop the machine. In practice, however, some of these defective parts would pass through the feeding devices and automatic workheads, but would not be assembled correctly and would result in the production of an unacceptable assembly. This is what I discussed last time. In this case, the effect of the defective part would be to cause downtime on the machine equal to only one machine cycle, meaning that assembly will be made, but it will be unacceptable. So, in one cycle one assembly we are making, since it is unacceptable, so therefore, we are wasting one machine cycle. The time taken to produce capital N assemblies, whether these are acceptable or not, this will be machine time plus downtime, this is the total time, this is what we have seen. Now, if m is less than 1, let us say not all defective parts stopping the machine, only about capital N minus 1 minus m x and n of the assemblies produced will be acceptable. What does it mean? Total number of assemblies we are producing n, and 1 minus m x n n will be unacceptable assemblies, okay, where the defective part goes in, it is assembled, we are losing one cycle time for one unacceptable assembly, but the assembly is unacceptable because the defective part went in, but it did not stop the machine. So, 1 minus m, therefore, if m is equal to less than 1, x n n is the number of unacceptable assemblies. Okay. The average production time TPR of acceptable assemblies is therefore given by the total time, okay, and the number of unacceptable assemblies produced, that is n total assemblies minus unacceptable assemblies. So, this is the total number of assemblies produced. So, this will be simplified, this can be simplified as t plus m x n t divided by 1 minus m into x in and n. Taking typical values of let us say x equal to 0.01, that quality level of parts is 0.01, meaning that out of 100 parts 1 part is defective. Cycle time is 6 seconds, for example, this is an example taken, and the time taken for an operator to diagnose the problem if machine stops and restart the machine is 30 seconds, and the number of automatic work heads will be 10. So, if you put these values in this equation, we will have the average production time TPR is equal to 30 into 2 plus m divided by n plus 9 plus m, putting these values here. So, if we draw the curve now for different values of m, okay, so we will get the TPR and the curve will be like this. Okay. So, in this axis we have the production time, average production time 6, 7, 8, 9 second. This is for this example, for this equation, and in the x axis we have the proportion of defective parts causing machine stoppage m. So, we have the m here and TPR, we will find out the TPR, it gives a straight line. So, what it says is that for a maximum production rate, okay, maximum production rate of acceptable assembly, m should be as small as possible. For small m, TPR is minimum. So, the production rate which will be 1 by TPR, it will be maximum. So, therefore, it is said here for a maximum production rate of acceptable assemblies, m should be as low as possible. This is one example, one conclusion that we can draw. In other words, when designing the workheads for an indexing assembly machine, when a high production rate is required, it is preferable to allow a defective part to pass through the feeder and workhead and spoil the assembly, rather than allowing it to stop the machine. You understand, we discussed it as last time that we have to find out whether machine stoppage is more convenient for us or more economical for us, or having an unacceptable assembly more economical for us. Here is the curve which says that the m should be minimum. Okay, m should be minimum means let it go, let it spoil the assembly. So, this is the one conclusion, second conclusion that we can draw. Effect of part quality on the cost of assembly. Okay. So, we said that part quality is higher, then the cost will be higher. The total cost CT of each acceptable assembly produced on an assembly machine is given by this. This is MT into TPR, TPR is the average production time, MT is the total cost of operating the machine per unit time, okay, and that includes operators' wages, overhead charges, actual operating cost, machine depreciation, these things we have discussed earlier. That means, the how much machine life you are using, how much money you are paying for to the operator, how much money you are spending for the overhead, that is the electricity, the building, the hydraulics, the pneumatics and so on, everything is included in this MT, plus C1 plus C2 plus C3 up to Cn. These are the number of parts. So, each part will cost some money. So, this is included here. Estimation of MT, for doing that we assume that a machine stoppage caused by a defective part will be cleared by one of the operators employed on the machine, and that no extra cost will be entailed other than that due to machine downtime. And if a defective part passes through the workhead and spoils an assembly, it will take an extra assembly worker Tc second to dismantle the assembly and replace the non-defective parts in the appropriate feeding devices. This is assumed. Okay. So, therefore, the total operating cost MT will be equal to M, some cost will tell you what is the cost, and into PU, TC and the WA, whereas this M is the cost of operating the machine per unit time if only acceptable assemblies are produced. WA is the assembly workers rate including the overhead, and the TC is the cycle time. All right. PU, which is the number of unacceptable assemblies produced per unit time, which is equal to 1 minus m into xn divided by t plus mxn t. This you can find out from earlier equations. Therefore, mt, which is equal to m plus this, we can find out the pu value from here, and we put this in this equation, the value of pu, we find this. In estimating the cost C I on an individual component parts, that is C 1, C 2, C 3 up to C n, it will be assumed that this can be broken down into two parts. One, the basic cost of the part, that is the raw material irrespective of the quality level, and the cost that is inversely proportional to x, and that will therefore increase with the better part quality. Meaning that one part cost is the basic material cost, and another cost is that when we are giving the value to the part, to the workpiece, and if the quality level is very high, the part cost will be very high. Thus, the cost of each part may be expressed as C I is equal to A I plus B by x. A I is the fixed cost, that is the raw material, and B by x, meaning that it will be inversely proportional to x. X is more, that means C I is less. So, therefore, it is inversely proportional, and B is the measure of the cost due to quality level, and for the purpose of the present analysis it will be assumed to be constant. This B will be assumed to be constant. So, the total cost C T will be M plus this plus unacceptable assemblies divided by this plus total number of parts that we have. So, each part will cost something here, and for the quality level of parts. So, we are adding all of them together and we are having this equation. So, this part we have seen earlier and from here it is coming. So, altogether we are trying to find out this C T, okay, which we have written here, find out the value of the MT, TPR we found out earlier, average production time, and C 1, C 2, C 3, C up to C n will have two components, raw material and B by x, that is inversely proportional to the quality level. Now, this equation, all right, this equation it shows that a cost that will decrease as x is reduced, a cost that is constant, and a cost that will increase as the x is reduced. Here, for example, if x is reduced, cost is reduced. If x is reduced, nothing happens because it is constant, is a raw material. If x is reduced, it will be higher. So, there are three different causes we can find out, and it follows that for a given situation an optimum value therefore of x will exist that will give a minimum cost of assembly obviously. Since in this equation the x reduction of x is reducing this, reduction of x is no effect, and reduction of x is increasing this. So, therefore, there must be an optimum value of this C t, okay, and therefore, an optimum value of the x. So, we will find out that for m is equal to 1, what this equation boils down to this, all right, and m here, capital M, I will remind you, is the cost of operating the machine, B is the measure of the cost due to quality level. So, for optimum value of the x, we will take the first derivative equal to 0. So, if we take the first derivative of this equation, you will find that this will be m n t minus n b x to the power minus 2, which will be equal to 0. So, x optimum will be b by m t to the power half, so root over b by m t. So, for a given assembly machine where m and b are constants, optimum quality level of part used in is dependent only on the time taken for clearing the defective part from a workhead, because B and M we assume to be constant. So, therefore, the optimum level of the part quality is inversely proportional to the root over T, and capital T is the time taken for an operator to diagnose the problem and restart the machine. So, this is the conclusion that we can make from this equation. Now, if we draw the curve for the parts, for example, for certain A and B values, in that case the cost of part here and the quality level here, the equation goes like this, meaning that as the quality level is here, the cost is, quality level, this is the number is increasing, then the cost will be decreasing. That means, the higher quality, the cost will be higher quality will be of this side. Okay. Now, putting the value of x optimum as B by MT root over, which we have found out in the earlier equation, we can see this, and from here we can find out these curves. These curves are made for cost of assembly and the quality level of parts, and you will see that there are different qualities, different costs, that is the cost of downtime, cost of quality of parts, cost of assembly, and altogether we will have a curve like this, where we will always have an optimum value of the quality level for which the cost is minimum. So, this is the conclusion which is drawn from here. Now, let us see, we have seen so far the indexing machine. Now, let us see the free transfer machine. I will simply give you a glimpse of the free transfer machine, what happens in comparison to indexing machine, and here what are the problems that exist. So, in the free transfer machine, we will always have the more number of parts, that is output will be always more, because one machine stoppage will not affect the other machines working, because there is a buffer stock in between. Okay. There can be an analysis made. So, to say that even for a minimum number of buffer stock, we will always have a more number of output in the free transfer machine in comparison to indexing machines, for example. Any workhead on a free transfer assembly machine will be forced to stop under 3 different circumstances. Suppose we have this as a free transfer machine. So, we have the workhead 1, 2, 3 and 4. In between the workhead, we have the buffer stock. Let us say the buffer stock maximum size is B, small b, and suppose in between we can have some buffer stock which is number A. Okay. If a defective part is fed to the workhead and prevents the completion of its cycle of operation, then the certain workhead will stop. Okay. Then an interval of T second, capital T second elapses before the fault is cleared and the workhead is restarted. That is one reason when the workhead can stop, that is a defective part goes in and an operator takes capital T time to fix it. Other reason is if the adjacent workhead up the line is to this, for example, if this workhead stops, then the supply of assemblies in the buffer stock between them, if it is exhausted, then this machine has to stop, because this machine stops means it is no longer supplying the sub assemblies to the buffer, and this machine has no way to take up the buffer from the buffer. So, it will stop. Third reason is that if the adjacent workhead down the line, for example, if this machine stops and the buffer stock is full, then if the buffer stock is full, then this machine when working, it cannot put the sub assemblies that here it has completed to this buffer because it is full. So, it has to stop. So, these are the 3 different reasons why any of the transfer machine in the line can stop overall. Performance of a free transfer machine will in overall we will see this is producing n assemblies. So, capital N into small x stoppages will occur when m is equal to 1, because all the machines will all the defective part will stop the machine. If each fault takes t seconds, so it will take downtime will be n, x and the t, that is the first workhead. Average downtime in second machine is the same as in the first machine, which is nxt, but a fault in the second machine will prevent the first machine from working for a period of nx into t minus b minus a into t second. Let us discuss it, what is that. A fault in 2 So, fault in 2 means that it will still supply it to the buffer till the buffer is filled up. Suppose here it is A1, we can have the A1 sub assemblies. So, B minus A1 till that time into T cycle time it can work, but then after that it has to stop. So, a fault in 2 will prevent 1 from working for a period of nx t minus B minus A into small t second. Similarly, stoppages of 3 will prevent the 1 from working for a period of, let us see, here there is a this is the third workhead. It will, if it stops, it will prevent the 1 from working up to 1, here it is B number, here it is B number B. So, 2B minus A1 minus A2, let us say here it is A1, here it is A2 number of sub assemblies into T, all right, and nxt. nxt is the total downtime minus this value nx into this value. So, overall it is nx, okay, in bracket T minus 2B minus A1 minus A2 into the cycle time. Now, the similar expressions can be made, can be derived from the effects of 4, okay, of the 4. I mean to say, see what we have done is, right now what we have done is the stoppage of effect of the stoppage of 1 on its own, effect of stoppage of 2 on the 1, effect of stoppage of 3 on the 1 and 4 on the 1. Similarly, we can do it for this station workhead, that is what will be the effect of defective part going in the second one, that will be nx and the capital T. What will be the effect when it stops on these 2, what will be the effect when the third workhead stops on the 2, and what will be the effect when the fourth workhead stops on the 2, and similarly for 3 and 4, that is what we are telling. So, similar expressions can be derived for all these 4 workheads. Therefore, the total downtime on 1 while producing n assemblies, total downtime will be 4 parameters, that is the nxt, this is the effect of the defective part going into that machine 1, this is the effect of stopping the machine number 2 on the 1, okay, on the machine 1, this is the effect of stopping the machine number 3 on the machine number 1, and this is the effect of stopping the machine number 4 on the machine 1. All right. Similarly, okay, from here we can find out that d1 by nx, this is equal to this expression, that we are simplifying. Now, this expression, it is for the workhead number 1, this is the downtime of workhead number 1. Similarly, we can find out what is the downtime for workhead number 2, what is the downtime for workhead number 3, and what is the downtime for workhead number 4. So, we can have d1 by nx, d2 by nx, d3 by nx and d4 by nx, okay, equation, same as we have done for the d1 by nx. Now, analysis is based on the fact that over a long period of time, the average downtime on each workhead must be the same, okay, because they will be equalizing. So, therefore, d1 is equal to d2, d is the downtime for machine number 1 is equal to downtime for machine number 2, machine number 3 and 4 and so on. So, therefore, all these 4 equations can be simultaneously solved to find out the values of A1, A2, A3, A4. What is A1, A2, A3, A4? Is that the number of parts, what is here is A1, number of parts A2, number of parts mean number of sub assemblies in the buffer. So, A1, A2, A3 in these equations we have here everywhere we have this. So, A1, A2, A3 we can find out by simultaneously solving these equations. Okay. Putting these values in the equations of d1 by nx, d2 by nx, d3 by nx and d4 by nx, like one of them has been shown here d1 by nx, and as you understand the similar equations can be derived for d2 by nx, similar for the machine number 2. For machine number 3 you can derive same way the d3 by nx and d4 by nx. So, there will be 4 equations, those equations can be simultaneously solved to get the values of a1, a2 and a3. When you are putting these values here, in case there is any negative value in the bracket, they have to be actually rejected. Okay. And then again those 4 equations have to be solved by rejecting that bracket parameter where the value is negative. Again find out the value of the a1, a2, a3 afresh, again put them in these equations, and again we have to test whether the bracket value is not negative. If it is negative, we have to repeat the process. Okay. Keep on doing that and you will find out the what will be the d for the overall the line, because as we said that overall what will happen is the d1, d2, d3 and d4 they will have to be same. Therefore, the small d is the downtime that we are finding out for the entire line consisting of these 4 machines, alright. If small d is found out, you can find out what is the downtime or proportion of downtime, because proportion of downtime is, as we said, that is the downtime divided by total time, and total time will be knowing as we have done it earlier, and therefore, we can find out the values. So, I hope it is clear that if we have, in this case we have actually given that example of 4 machines 1, 2, 3 and 4. So, the number of machines can be much more than that, and the way of finding out the d, which is the downtime, is the one that we have described, be it 5 machines or 100 machines, the same way you can find out. Once again, the basic thing is that we have to say that what is the effect of each of them. I will repeat once again so that it could be clear that when you are considering the workhead 1, finding out the downtime of workhead 1, you have to find out 3 things, that the effect of this workhead itself when a defective part goes in, that means nxt, alright, capital T is the time taken for diagnosing the problem. Then what is the effect of stopping 2 on the 1. So, in this case since there are 4, so there would be 4 parameters, effect of stopping 3 on 1 and effect of stopping 4 on 1. Similarly, when you are for example say analyzing or finding out the downtime for workhead number 2, you have to find out the effect of the defective part going into the 2, that is again nxt the same, but then there will be effect of stopping 1 on the 2, and once again I will tell you that if the 1 stops, in that case 2 can still work, because there are sub assemblies in the buffer stock, it can take from the buffer stock till the buffer stock is empty. So, buffer stock, suppose there are A1 number of parts. So, B minus A1, B is the buffer stock volume, maximum number that can be taken. So, that will be the time into t into small t, which is the cycle time, that is the time till the 2 can work if the 1 stops. Now, for example, if here I will repeat it once again from here. Now, stoppage of 3, let us say stoppage of 3 will prevent 1 from working for a period of this much. Okay. So, when we are talking about the stoppage of 3, we will have the effect from this buffer and also from this buffer. So, therefore, what we have considered is this 2b minus a1 minus a2, and that will be till the cycle time small t it will work, and therefore, the stoppage of 3 will prevent 1 from working for a period of nx capital T minus 2b minus a1 minus a2 into t second. So, overall what we are saying is, suppose you have a large number of machines, in that case although it will be difficult, but you have to consider the effect of stoppage of all machines on that machine for which you are actually considering the downtime. Okay. One thing I would like to repeat once again here, that how any workhead on a free transfer assembly machine will be forced to stop under 3 different circumstances. Okay. See, for example, here this is I am repeating once again for clarity, because this is somehow little difficult to understand. Suppose you have a workhead here, all right. Now, a defective part goes in in this to the workhead and prevents the completion of its cycle of operation. All right. Then an interval of capital T time will be spent, elapses before the fault is cleared and the workhead is restarted. Now, suppose this is up the line, okay. This is up the line and this is down the line. Okay. Now, if the adjacent workhead up the line, this one up the line, if it stopped and the supply of buffer storage between them is exhausted, there is none. So, in that case this machine will stop because it cannot take any subassembly from here, it is empty. So, that is the second reason. Third reason is that if the adjacent workhead down the line stops, for example, if this machine stops, in this case this machine can work and put this subassemblies in the buffer till the buffer stock is full. Okay. So, if the adjacent workhead down the line has stopped and the buffer storage between them is full. So, I hope this is clear. I have repeated that and this is little difficult to realize. Okay. So, that is what I wanted to describe, I wanted to discuss in this course of manufacturing automation. Thank you for your attention.